4.4 Conservation of energy for a control volume. The first law of thermodynamics states that energy cannot be created or destroyed. For closed system, the first law of thermodynamics can be written as delta E equals Q minus W. So E is the all forms of energy in the system, and Q is the heat transfer across the system boundary. W is the work across the system boundary. So it may be used for any closed system and in any process. The energy equations may be written in the rate form. So dE over dt equals Q dot minus W dot. So this is the energy balance equations for closed system. If there is mass transfer across the system boundary, the first law of thermodynamics will have additional terms. In open systems, mass flows across the system boundaries. And this is the physical meaning of energy balance for open system. And this is the additional terms related to the mass transfer. So mass carries energy. The energy carried by the mass consists of two parts. The expression in this blue box is the energy associated with the fluid. So the fluid contains energy in different forms, including the internal energy, kinetic energy, and potential energy. M dot, the mass flow rate at the inlet, mass flow rate at the exit. V is the velocity, Z is the elevation of the system. So these relations indicate rate of energy transfer into the control volume accompanying mass flow. This part indicates the rate of energy transfer out of the control volume accompanying mass flow. And the second part of the energy carried by mass is called flow work. So the flow work is the work required to push the fluid into the system or out of the system. So the fluid going into the system is pushed in by the fluid behind it. Or imagine a piston to push the fluid into the system. And this flow work corresponds to m dot I times Pi times Vi. In the same way, when the fluid is going out of the system, the fluid is pushed out of the system by the fluid behind it. And this kind of work is called the flow work. This flow work corresponds to m dot E Pe times Ve. And the flow work is expressed as P, pressure times specific volume. So we know that work can be expressed as the force times displacement. And the force in the flow work is the pressure times area. Area is the cross-sectional area of the fluid. So force times displacement. And area times displacement is volume. So work is pressure times volume. Therefore, flow work can be expressed as the pressure times specific volume of the fluid. So these terms in blue boxes are the energy carried by mass. The work for the open system has two parts, flow work and all other energy transfer by work, such as electrical work and shaft work. And based on these two relations, and we can write these equations. So internal energy, flow work, kinetic energy, and potential energy. So this is the energy of a flowing fluid of mass m. And for convenience, we combine the internal energy and flow work, and it's called enthalpy. So enthalpy is the sum of internal energy and flow work. This equation looks complicated, but it is often further simplified with appropriate assumptions. The change in kinetic energy or potential energy may be neglected, and the system may operate in steady state conditions. dE over dt may be 0. For multiple inlets and exits, we use summations to include total energy transfer across the system by mass. Four point five. Analyzing control volumes at steady state. At steady state, the properties do not change with time. So there is no change in mass of the system with time. This means that the mass flow rate going into the system equals mass flow rate going out of the system. So left hand side term dE over dt is 0 at steady state condition. For one inlet and one outlet system, this term indicates the change in enthalpy of a fluid, change in kinetic energy of the fluid, and change in potential energy of the fluid.